All right, so let me just quick write down statements for each of the kind of big name theorems. So what's your favorite?
Greens.
Greens? Because it's two-dimensional, right?
Yeah.
Okay, so Greens, important facts. It's 2D, right?
Mm-hmm.
It applies when things are flat.
And then non-simple.
Flat has along an axial plane.
In the XY plane.
Only the XY, not the YZ.
You could, of course, modify it to apply, but the way it's stated, it applies only in the XY plane. So this only works on two-dimensional objects.
And it also has to be a closed but not simple curve.
Perfect. I need a
Oriented
closed,
counterclockwise.
simple curve. And really, in all of these, you can assume that everything I'm saying needs to be at least piecewise smooth. If it's not at least piecewise smooth, none of it's going to work.
And oriented counterclockwise. Right?
Yep, so oriented counterclockwise. Bounding. Maybe I should name this thing. Let me call this thing C. And this thing's bounding what? Some region D. Or R, or whatever. Yeah, doesn't matter.
Let's say that this 2D object is in the ZY plane. Can you just swap Z for
Yeah,
X?
you can just do variable substitution, right?
And it needs endpoints, right? Is that what you said?
Paths need endpoints.
Okay.
This thing needs to be closed. So it's got to be a loop. And in fact, it's got to be a simple loop. So it's got to be a loop that doesn't cross itself.
Because on my test, I didn't know you were just asking for simple lines. You wrote needed to be endpoints.
Yeah, I was asking for paths.
Okay.
Paths have a start and stop.
Okay.
So I've got a simple closed curve counterclockwise bounding the region D. So that's a picture like this, right? Here's a curve, here's a region D. And then what do I know about this thing?
The circulation along the curve C.
Is equal to curl the.
Okay, circulation around the vector, or circulation of the vector field F around the curve C is the
curl of F.
yeah. So curl of F, right? Two-dimensional curl. I would need to integrate over D area.
And it's not a DA with the vector hat.
And it's not a DA with a vector at it. Why?
Because there's no dotting across it.
Yeah, because this is 2D curl, which is a scalar thing, right? You guys all see that? It all points either up or down, and it's just the sign that takes care of up or down. Cool? So what's the 3D analog?
3D
Stokes. Okay, so if I wanted to think about Stokes, I might really think about Stokes as 3D greens. Right?
Yeah.
Really, maybe it would actually be better, and a more honest mathematical phrasing is to think of greens as 2D Stokes. But we learned greens first, so Stokes feels like a slight upgrade, and that's really what it is. So what do I need for Stokes?
Closed
Need a
surface.
Closed.
Can a surface be simple?
I need a closed simple curve, at least.
Oh, right.
Right? And it needs to be piecewise smooth again. Bounding. What? What am I bounding?
Some floppy region.
Yeah, some floppy surface. And again, this surface S needs to be at least piecewise smooth. Okay, so I've got a curve bounding a surface. So that looks like this. Here's your surface. There's your bounding curve. Something about orientations. What's the orientation thing?
Right hand.
Oh,
Yeah, remember there's really only one tool for orientation in Cut 3, it's the right-hand rule. So I need the orientation on the curve to match the orientation on the surface, right hand rule.
Put your left hand over it, you'd be over the surface.
Yeah, so if I was walking along it, my left hand would be over the surface, or if I wrapped my fingers on my right hand through the bounding curve, my thumb would point in the orientation of the surface. Cool that?
So, sorry, I was going back to green, so the counterclockwise could also be the right hand rule.
Yeah, in fact, the counterclockwise is the right hand rule with up being the thumb. Okay, so I've got right hand rule orientations. And what else? What's the result? What do I get?
Circulation around curve, along the curve.
Along the surface.
Okay, so I get the circulation of a vector field F along the curve is
Integral of the surface.
Same thing.
the integral over the surface of the curl of F. And now I need a,
dV. Oh no, that's for the divergence.
yeah, it's got to be an area, right? But now this curl thing, right, is a vector field. So I need to dot product this with the area. You guys see that?
Now it has a vector hat.
Yeah, now it has a vector hat because I'm having to dot product to get a scalar that I can actually integrate.
And what does that d area vector equal?
So that d area vector, right, we have a couple forms for it. Maybe the function one is the most useful, which is this minus fx minus fy and 1 dx dy.
So we can still use those, didn't we use those in flux integrals?
Yeah,
So we can still use
because
those.
that's what we're calculating.
A flux.
This thing is a flux integral. This is the flux of the curl function through the surface. Remember the curl function is that little paddle wheel thing? So if it's pointed along the direction of the surface, what that means is that there's some circulation in the surface happening.
And now
Right.
we're dot product.
There's some little spinning in the surface. That means there's going to be circulation around the outside edge. Right? I'm adding up all the tendency to eddy, and I'm getting the motion around the outside edge. Same thing here, right? I add up the tendency to eddy, and I get the motion around the outside edge. With the help I'm getting going. Cool? Is with that? All right, and divergence, which I'm gonna kind of cram in a corner here, even though it doesn't deserve it. The divergence theorem is the easiest one of these, and one of the slicker ones. So what do I need for the divergence theorem?
The divergence of F.
Okay. Divergence of F.
There's your variables.
Oh, the integral.
We go
over
to
the
infinity.
surface.
So I need the integral over some region d volume.
Yeah.
So if I add up the tendency to spread through a region, what do I get?
How much is leaving?
Yeah, I get how much is leaving through the outside, right? So I get the flux through the surface. And what's the setup for this?
Just has to be
Um,
closed.
Perfect. I need,
surface, smooth surface S.
okay, smooth S bounding
Region.
region R. Okay, what else? I need anything else?
Does it still give you an oriented formula? Oh, counterclockwise.
Okay, so one of these things needs an orientation, the other one doesn't.
The one on the left does.
Yeah, this needs an orientation, right? You guys see why this one doesn't?
It's just a shape.
And numbers.
Yeah, this is just a number thing, right? This is a scalar integral. So this guy needs an orientation. If I'm adding up the divergence, right, the tendency to leave, Which way should the surface S be oriented? In or out?
Outwards.
Should be out, right? So oriented out. Let's see, what else do I need here?
What the divergence function is, kind of.
Yeah, I need to be able to calculate the divergence function, right? So I need this thing, F, to be smooth, which is actually true for all of these, right? That vector field F has to be smooth. What else do I need? There's one more assumption on here that's a little bit crucial, but it's a little strange.
Cross it with the weird empty partial.
No, that's going to be calculating this.
Divergence.
This will be dot. But
Or dot, yeah.
here, I want you to note one thing. This region R has to be bounded, which I can't spell for some reason right now. If that thing's not bounded, this isn't going to work. You see that? If I had a region, for instance, that was a cylinder, right? That ran off in both directions. If I was trying to tell you something about the flux through this surface, and I add up all the divergence in here, what if stuff just flows to the left? You guys see that? Maybe it would be even better if I just put a cap on this sucker. Right? If I just had a vector field that does nothing over here and then over here flows off, that's right. If I had a vector field that just kind of flows off to the right faster and faster, the divergence in here is going to be pretty big, right? But nothing's actually passing through the surface, it's just running off the right-hand side. You guys see that? So this region R has to be bounded.
And then the condition where it has to be a continuously differential vector field?
Yep, so all of these have to be a continuously differentiable vector field. Otherwise, none of these three theorems work. And that's really because I'm going to take a partial in each one of them, right? You guys see that? I'm going to take a partial here when I do curls. I'm going to take lots of partials here when I do three-dimensional curls.
So they, when they say continuously differentiable, they mean differentiable like around the.
Yeah, so they mean,
But not infinitely differentiable?
they mean differentiable once and the derivative is continuous. And then on all of these, it has to be in a slightly bigger space than you're talking about.
Yeah.
You guys see that? So like here, I've got some, maybe ball-shaped thing. This one doesn't work. Some like blobby business like this. It's oriented outwards. The region R is the inside of it, right?
Yeah.
I would have problems if my vector field had differentiability issues right here on the edge. Right? That would cause me problems. But as long as the differentiability issues are like out here, I'm totally fine.
It can be any distance, right? Any distance away from the surface.
Yeah, as long as there aren't lots of them coming together onto the surface. Right, as long as they're not kind of bunching up next to the surface.
Okay.
Right, there has to be a defined area
Yeah.
from this thing out to the nearest one. Do you see that? And then, so I have Green's, Stokes, and the Divergence. These are the big three. These are all actually versions of Stokes in some reasonable way.
How does divergence relate to Stokes?
It's hard.
It just seems totally different.
Yeah, it does. The calculation's different.
Yeah, so what we're doing, right, is we're passing from an integral of an object to the integral of the boundary of the object. You guys see that?
Okay.
Like that's what all of these do. And I take some kind of a funny derivative of a vector field, right? So here, I'm doing the exact same thing, right? I'm passing from the integral of an object to the integral of the boundary.
But you're
And here I've got a funny derivative of a vector field.
figuring out how much is leaving in that.
Yeah, this one feels a little different, and that's okay. But really, all of these things boil down to the idea of I've got an integral over some kind of region, of, over the boundary of some region of a vector field for some object, right? And really I'm turning this into a region over the not boundary, and I'm putting the derivative thing on this guy. You guys see that? This should feel a little like integration by parts. Right, you're trading the derivative from one thing onto the other thing. You guys see that's how integration by parts really works?
Yeah.
Right, you start with u dv and then you turn it into some junk and then a v du. You're trading derivatives there. That's really what I'm doing here. I'm trading a space derivative for a vector field derivative. If you go look up Stokes, like if you look up Stokes on Wikipedia, this is the form you're going to find. That's full-blown vector like manifold calculus Stokes. We teach it to you in 3 kind of different pieces because they're a little more digestible.
Does Stokes apply to like 4th and 5th dimensional?
Yep, absolutely, and it works exactly this way. Cool. And then the other thing that looks a little bit like this is this fundamental theorem of line integrals, right? What's the difference between the fundamental theorem of line integrals?
That gives you.
Yeah, good. The path doesn't have to be closed.
And we're parameterizing in some.
Yeah, we usually parameterize to get them, right? They're a little bit different.
Or use the gradient.
Yeah, so the fundamental theorem of line integrals, fundamental theorem of line integrals. And I'm just kind of throwing this in the margin because really this isn't quite one of these guys. It's close. It's really maybe almost. I should stop talking about it. What am I doing? I'm integrating the gradient of some vector field.
Yeah.
Right? dr. And what do I get?
F of Q minus F of P.
Yeah, I get f of b minus f of a, where c is some path that goes from point A to point B. In some sense, you're right. You guys see that? I'm really taking an integral of a derivative of something, integral, a derivative of something, and I'm trading it for the integral over the boundary, which is just the first end minus the second end minus the first end. Right? It's weird to integrate over 2 points. But
If this is closed.
yeah, if this is closed, right, this says if you integrate a gradient over a closed curve, you get 0. Why?
Something perpendicular or something.
How about they're path independent?
Oh yeah.
Right? Remember gradients are path independent vector fields?
Yeah, they are.
So I can just kind of think about, okay, I've got a loop. What if I just shrink the loop down to nothing? Should give me the same answer the whole way along. Cool. All right.